Hello everyone. This video demonstrates the experimental section of our work published at IROS. In this work, we propose GP-MPPI, an online learning-based control strategy that integrates the Model Predictive Path Integral control algorithm, MPPI, with a local perception model based on Sparse Gaussian Process, SGP. The key idea is to utilize SGP's learning capability to construct an uncertainty surface, allowing the robot to learn about its surrounding navigable space, identify suggested subgoals, and recommend the optimal subgoal, G*, for the MPPI planner. Then, MPPI computes the optimal control sequence that satisfies the robot and collision avoidance constraints. Such a proposed approach eliminates the need for a global map of the environment or an offline training process. We validated our algorithm in both simulation and real-world setups. For simulation, we used a challenging maze-like environment, where the robot has to perform two missions, labeled as MU1 and MU2. During MU1, the robot must navigate from the environment's lower left corner to the opposite corner, where the goal is at a U-shaped obstacle, as shown in Figure A. While during the second mission, MU2, the robot has to navigate through a U-shape to reach the goal, as displayed in Figure B. In this study, we introduced two operating modes for the GP-MPPI algorithm, the simple mode and the recovery mode. Under the simple mode, MPPI consistently leverages the optimal subgoal, G*, suggested by the GP policy. In contrast, in recovery mode, MPPI generates the optimal control sequence that steers the robot towards its desired state, adhering to the recommended subgoal only when the robot is at risk of encountering local minima. Take, for example, the robot trajectory shown in Figure B, where the yellow color indicates the trajectory segments where GP assisted MPPI in avoiding local minima. Here, we present the simulation results of our proposed GP-MPPI control strategy for the MU1 mission, showcasing the two operating modes. We can clearly observe that our proposed control strategy successfully achieves collision-free navigation in both modes, without getting stuck in local minima. Moreover, activating the recovery mode during the MU1 mission improves the average distance traveled by the robot. In this trial, the assistance provided by GP to MPPI when the recovery mode is utilized exceeds 42%. Here, we are rerunning the simulations for the second mission, MU2. During this mission, the recovery mode produced a slightly longer robot trajectory than the simple mode, since operating our proposed approach in the recovery mode strikes a balance between the state-dependent cost function directing the robot towards the desired state and the optimal subgoal suggested by the GP policy, which forces the robot to avoid the dead ends associated with the two rooms on its way to the desired pose. The next simulations show the performance of the vanilla MPPI and log MPPI in a given maze-like environment. We can see that both control methods were unable to complete any of the assigned control missions due to the challenging environmental conditions. Finally, we experimentally demonstrate the applicability of our proposed control strategy in a complex and unknown L-shaped indoor corridor environment. We can conclude that both operating modes ensure collision-free navigation in the given environment with an average linear velocity of 0.8 meters per second, without the risk of being trapped in local minima while moving towards their desired state. However, the two baselines failed to complete the control mission due to getting trapped in the first edge of the L-shaped environment. Thank you for watching.